Hello, my name is Felipe Viana, and today I want to talk about the work done by my research group at the University of Central Florida. As you see, it has to do with building hybrid models that combine physics and machine learning. I'm the principal investigator at the Probabilistic Mechanics Lab. I've been at UCF for 2.5 years now, and I teach dynamics, vibrations, and controls at the undergrad level, as well as probabilistic methods and multidisciplinary optimization at the graduate level. Before joining UCF, I spent roughly 7 years in industry working with design and services of jet engines and wind turbines. All the good work that you see here today have come from the hard work of my Ph.D. students. I have a lot to thank them as well as the sponsors and collaborators that make our research possible. So the first thing that I want to talk about is physics-informed machine learning. There's a series of papers that we've been publishing. I have all these papers available on my website. Here's the link if you want follow along. So hybrid models is the core of the physics-informed machine learning that we perform in our lab. It has to do with addressing challenges that are specific of physics-based models. So let's take, for example, fatigue crack growth, which is highly dependent upon the accuracy of finite element simulations. The problem with models for this particular application is that the mesh refinement and the level of understanding of loads that are needed for accurate estimation in real applications like aircraft engines or wing panels of aircraft is just high, and it makes the computational cost untreatable. So this is one problem with regards to the modeling part. The other problem with regards to modeling is that the input data needed for this model is available throughout long histories of time, years of operation. Nevertheless, the output for these models is not necessarily available. Sometimes you have inspections that happen in frequent periods of time. Sometimes you don't. So with that, it becomes very hard to estimate parameters for the models that you're building in such a way that you reduce the gap between predictions and observations. The idea that we developed in our lab is, what about mixing within neural networks, mixing kernels that are physics-based so that we reduce the need of large data sets when training these neural nets? On the flip side, what about we use the capability of the neural net to learn the discrepancy between observations and predictions? In a way, you take the best of both modeling approaches. So we do that by using state-of-the-art neural network architectures like the recurrent neural network that you see on the right-hand side. And then we design these recurrent neural networks to mix physics with data, physics kernels with data-driven kernels. In this particular example here, we have in blue the fatigue damage accumulation out of coupon tests that you get based on physics, with a stress intensity estimation that you get out of data-driven layers. Using this concept, we've been applying the idea in different applications. I decided to show 3 that I find interesting. The one on the left-hand side is a proof of concept that we first published a while ago. And it has to do with this idea of estimating a block in a series within this recurrent neural network cell, as you can see here. And even though we trained this model with only 15 airplanes with observations for the output crack length at the end of the 5th year only, we were able to predict fatigue crack length on a large fleet of airplanes, about 300. The other application that we developed was this idea of compensating for uncertainty in the physics of failure such that there is a competing failure mode. And in that way, it's almost as if you can think about a parallel compensation within the damage accumulation cell. In this case, let's assume that you understand the mechanical fatigue component of your physics of failure, but you're not fully aware of how the corrosion fatigue portion of the damage accumulation works. And then you do that through data-driven layers within the recurrent neural net. So again, we trained with a few data points. In this case, I think it was 10 airplanes. And then we predicted on a large fleet. I think that in this case, it was about 150 airplanes or so. The last example that I want to show here is yet a different application. In this case, it's lifing, fatigue lifing of a main bearing that sits on a wind turbine. In this case, you have the mechanical fatigue happening at the bearing, and then you have the degradation of the grease that is within this bearing and has the intent of lubricating the bearing, which you don't know much about the physics. And then you model that with a data-driven layer within the recurrent neural net. And then you can see the results on the bottom here where you reduce that gap between prediction and estimations when you build the hybrid model. So this has been very interesting, and there's a few papers that we publish on this. But it's not the only thing that we do in our lab. The next topic that I want to talk is about using Bayesian methods to understand LCF testing. And LCF would be low cycle fatigue, and how to optimize the resources while conducting LCF coupon tests. Again, we've been publishing papers on the topic, and you can find links to these papers within our webpage. So the motivation behind this goes with the design that you take this coupon data, build curves, and then you use these curves to perform design of critical components in, for example, gas turbines. The application would be here in this case. If you go by standard least square models, you can get a confidence estimate and uncertainty estimate. The problem is that it becomes, for the most part, conservative. With our proposed Bayesian methods, we have developed a non-stationary uncertainty model that once you feed through the Bayesian method, you can see that you reduce that uncertainty. And by reducing that uncertainty, you reduce conservatism needed in design. You can see that in one of these strain ranges, we reduce the uncertainty by quite a few cycles. So how does that help with optimizing the coupon test? So every time that you have one of these data points here in this plot, you create a coupon and you cycle that coupon all the way to failure. It's okay if you're cycling through 100 cycles, maybe even 1,000 cycles, but it becomes very time-consuming, tedious, expensive when you're doing 100,000, 1,000,000 cycles. So what we believe you can do is you can use these uncertainty models to forecast what's the range of cycles that you should observe. Now, if you use the Bayesian methods that we've been developing, you'll be able to reduce the uncertainty about those prediction intervals and therefore optimize the resources as you're planning this coupon tests. So in summary, I covered two of the most exciting research topics that we have in our lab: physics-informed machine learning with applications in prognosis and health management, and then optimizing low cycle fatigue test with examples in Cornell 617 and hashtags ally. A lot of the papers that you saw here have links available in our website, but we also produce code, and we make our GitHub available in case you want to download and check it out. Going forward, I'm very open for collaborations, especially if it has to do with the machine learning methods and applications. And then the emphasis is actually on applications. Our group is very keen on understanding different problems and how we can bring together the physics and the machine learning aspects to reduce uncertainty and optimize resources. So with that, I would like to thank you for your attention, and please feel free to reach out if you have any questions. Thank you.